Done.
Done, I
Can you
think, yeah.
proceed?
Can you make me co-host because I can start recording also then? Good afternoon, Bhatia sir. Yeah. So, good afternoon, everyone. We welcome you all for today's second lecture in the series of atmospheric dynamics and its applications to climate sciences. Today, Dr. Professor S. Baidya will be giving lecture. And before his introduction, I would request Someshwar Das sir, who is Secretary SAMA, to give his welcome address.
Thank you, Dr. Rohini. Namaskar, everybody. I'm sorry for the late because my laptop was hanging. Professor Tyagi Saab is the president of SAMA. Today, he has not been able to join yet. So, starting with Professor D.B. Bhaskar Rao, sir, senior most professor or honorary professor at Andhra University, Voltaire in India. Today's distinguished speaker, Professor Somnath Baidya, head of the Department of Center for Atmospheric Sciences at IIT Delhi. Our colleagues, organizing committee members, Dr. Rohini, Dr. Swagata, Dr. Dibya, all the distinguished participants from more than about 47 countries. Ladies and gentlemen, I welcome you on behalf of the South Asian Meteorological Association and Savitribai Phule, Pune University, India. As you know, this is the fifth lecture series on atmospheric dynamics and its applications to climate sciences, being jointly organized by SAMA and SPPU for the capacity building of the people of South Asia and the member countries of Non-Aligned Movement, NAM. Many of you know that we have conducted 4 lecture series earlier, and this is the 5th lecture series. Our earlier lecture series were on atmospheric physics, followed by a training on WRF modeling system, which was followed by a lecture series on satellite meteorology, and that was followed by a training lecture series on radar meteorology, and they all went on each for about 26 weeks. And this is the 5th lecture series, as you know. In today's lecture series, we have got about as of last night, there were more than 1,100 candidates registered for this course. So, as you know, the syllabus of this lecture series has been designed based on the feedback and requirements of the member countries of SAMA. The lecture series is targeted at postgraduate students and professionals of non-meteorological backgrounds who are interested in learning the atmospheric dynamics and its applications to climate sciences. This lecture series, as you know, will continue for about 6.5 months. That's about 26 weeks plus 2 more weeks for the final evaluation test and the valedictory session. So, supposed to end on 2nd of August 2025. As I said, although more than 1,100 candidates have registered so far, but the number is still increasing. And we will allow them for 1 or 2 more weeks because as per our rules, there has to be at least 75% attendance of the participants to be able to get the attendance certificate. So after 4 lectures, they will not be able to attend more than 75% lectures. So we'll close the registration after that. Also, as I mentioned, it was mentioned in the brochure itself that the prerequisite for this course is a good knowledge of mathematics and physics. And this course itself is a prerequisite for learning numerical weather prediction and climate modeling and prediction. Therefore, please be regular, please be attentive and try to watch the recorded videos on the YouTube channel, which are always available. As you know, this is a very tough subject for most of the people. Atmospheric dynamics, or we also call dynamic meteorology, is one of the fundamental subjects of the MSc and MTech students of meteorology and atmospheric science in the universities and institutes, and many students find it difficult subject. And also very few teachers prefer to teach this subject, by the way. So, however, this is one of the most important subjects, as I said, and is a foundation for the NWP, that is numerical weather prediction and climate modeling. We are fortunate to have a panel of senior scientists, professors from reputed institutions of this region who are experts in the fields. They will teach this subject with emphasis on its applications to modeling and prediction of extreme weather systems, short, medium, and long range and seasonal and climate predictions in different scenarios. They will explain how atmospheric dynamics is important for understanding the evolution of atmosphere and mesoscale systems like thunderstorms, cyclones, and in air pollution modeling studies. So, as I said, be attentive because we need your attendance of 75% to be able to give you certificate at the end. And also at the end of the lecture series, we will conduct a online test. And those who will appear in the test and also score good, then based upon their score, they will be also given certificates of outstanding, excellent, very good, good, etc. Okay. So the lectures, as you know, are live streamed on the YouTube channel of SAMA, and they will also be available afterwards, as I said, on the YouTube for those who could not attend because of the time difference between India and their countries. So please ask questions if you have doubts in the question and answer box, and have more interaction with the speaker. The question and answer will be answered by the speaker at the end of the lecture. It will be taken up by our organizing committee members, moderators. So have a nice time and good day. Over to you, Dr. Rohini.
Thank you, sir. Now I request Dr. Mili Ghosh Nilala to please introduce our today's speaker.
Thank you, ma'am. Please share the screen.
Once I will share.
Yeah, thank you. It's my pleasure to introduce Dr. Professor S. Baidya Roy. Dr. Somnath Baidya Roy is a professor and head of the Center of Atmospheric Science at IIT Delhi. He also holds the Rockefeller Foundation Climate Science and Technology Chair position. His primary research area is modeling land atmosphere interactions. He also works on renewable energy meteorology, including resource assessment, forecasting, and impact assessment for the wind and solar energy sector. He is a founding director of Tensor Dynamics, a weather and climate analytics startup incubated at IIT Delhi. He has completed his BSc in physics from Presidency College, Calcutta, MSc in environmental science from JNU Delhi, PhD in environmental science from Radboud University, USA. He has a list of honors in his name. He has completed his postdoc at Princeton University. He has worked as research associate at Duke University and also as assistant professor at University of Illinois, USA. He is chief editor of Earth System Dynamics, a leading journal of the European Geoscience Union. And he has total 117 publications in reputed research journals. 4 candidates have already got a PhD under his guidance and 5 are ongoing. We welcome you, sir. Thank you.
Thank you, Dr. Mili. I request Professor Baidya Roy, sir, to please share his screen and can start the lecture.
Okay, thank you. Thank you for that very generous and kind introduction. And I congratulate SAMA for organizing this and also the previous few lecture series that I have been a part of. It's very heartening to see like thousands of students and enthusiasts from across the world joining. And obviously, the role of Professor Dash and Dr. Tyagi obviously is commendable. So, and also I would say I am hearing about the non-aligned movement after a long, long time. So it's unfortunate many young people don't know what it is. And I wish we had something like this today, looking at the world today. Anyway, so I will not talk about politics. I will go straight into meteorology. Allow me to share my screen. I hope it is visible to you now.
Yeah, yes, sir, it is visible.
All right, thank you. Thank you. So I will get started. So welcome everybody to this lecture in atmospheric dynamics and its applications in climate sciences series. I believe you've already had two of atmospheric dynamics. But today my turn is like to introduce the technical aspects of the subject. As Dr. Someshwar Das mentioned earlier, that this is considered the most difficult of subjects for people who are interested in atmospheric and climate sciences. I think it's difficult, yes, of course, but I think it is also the most interesting. And so it will be our job, like here, people who are giving lectures, to bring out that most interesting side to you. So I will start with this animation, which I hope you can see. So this is just something that I just captured right now, like about perhaps half an hour back. So this is showing the global flow at the surface. And then we are seeing now the flow at the 500 millibars. And soon, yeah, right now the flow at 10 millibars, that is very high in the atmosphere. So if you look at these flows again, which I'm going to run this one more time, you will see that near the surface, we have the cyclonic and anticyclonic convergences and divergences, like here, then also over the Pacific, you can see in the Southern Ocean, Southern Pacific. But when we go high up in the atmosphere, then we see these strong kind of wave-like structures, both in the northern and in the southern hemisphere. But as we go high, even higher up, the waves are more or less gone, and it's kind of like either westerly and easterly flow. So, like, just at different levels in the atmosphere, the flows are very different. So that's very interesting. And so you will think that, okay, the atmosphere must be behaving very differently depending on the levels, and they do. But surprisingly, the equations that we use to describe this flow are the same, be it near the surface or the or the top level. So that is the beauty of atmospheric dynamics, that the same set of equations are able to explain this much broad level of complexity. Okay, so if you stick around till the end of the lecture, you will perhaps be able to understand why that is and appreciate the beauty of this discipline. Now, I will, sorry, I will not be able to do cover the entire thing today. I have been given the task of starting you off. So all of you, I have understand some fundamental knowledge of mathematics and physics. So I'm going to use the basics of vector algebra and vector calculus. I will just introduce them to you today and show you how these concept atmosphere. So many of you, like when you look at textbooks, you will see a diagram like this, force balance, or this is somewhere up in the atmosphere. If you look at boundary layer, if you look at other levels, even if you look at oceans, there are these kinds of similar forces. And if you look at how these forces are represented, you see that we use vector algebra and vector calculus to represent the forces. That is why it's very important to have a solid understanding of vector algebra and vector calculus to understand the forces in the atmosphere and understand the beauty of atmospheric dynamics. Now, I will not have time to go into the basics. This is just to kind of like recap what you already know. So some of these things will be very simple, but I apologize. I just think that we need to at least talk about them at the beginning so that we can connect them with the physics. So unless we use mathematics and understand the physics behind the mathematics, we will not be able to do justice to dynamics. So we all know what are vectors. Vectors are just quantities with both magnitude and direction, written with a bar or a hat or an arrow on top. And so they can also be expressed in terms of components, because we are dealing with a three-dimensional spatial field. So that is why we have three components: I in the x direction, j in the y direction, and k in the vertical. Often when we look at, like, spherical dimensions, or we look at the earth, this x direction represents west to east, y represents north to south, and k represents vertically upwards. So, for example, when we talk about horizontal velocity, so it's 2I minus 3j. Recall that because this is horizontal, this tells us that there is 2 units of velocity going in the from west to east, 3 units of velocity going from north to south, and the resultant velocity is a resultant of these two vectors. Because this is negative, that means it is going from because this is negative, it is going from north to south. It's south to north, positive. There is no k here. That is because this is horizontal velocity with no vertical component. Another good example is gravity, which only has k. There is no horizontal component because gravity works vertically downward. So this is how we represent vectors in the atmosphere, and the magnitude is just the square root of the sum of squares. Again, very basic. Again, other basic concepts: vector multiplication. So we start with the dot product or the scalar product represented with a dot, and that is given by AB cosine of theta. The outcome of this dot product or this operation is a scalar. On the other hand, we can also have a cross product where we multiply two vectors, and using this cross symbol, that the magnitude of that outcome of the resulting vector is AB sine theta, where theta is the angle between the two vectors. But the product is, this product is a vector, and M represents the direction of the vector, which is in a direction perpendicular to the two vectors. If you ask me, I personally like to use the matrix determinant method. This is something you are again familiar with, to estimate the estimate the cross product. So I can calculate the different components in all three directions. Now, obviously, this being calculus, vector calculus, we need to know about derivatives. So how do we calculate the derivative of a vector? We know how to calculate the derivative of a variable, right? But how do we calculate the derivative of a vector which has three components? So this is the derivative of a vector. Now, because of lack of time, I'm not going to be able to write this through. So this presentation will be available to you later. Textbooks have been recommended. So this lecture is supposed to kind of, or the textbooks will supplement what we have in this lecture. But I hope you will just take the time to understand the concepts that I'm going to explain here today. So if we look at a derivative, you will see the first three terms are the derivatives of, so here I'm taking a derivative of vector A with respect to S. So the first three terms are derivatives of AX, AY, and AZ with respect to S. The next three terms, almost like a product rule, are derivatives of the vector unit vectors themselves. So this is important because vector has both magnitude and direction. So when I take a derivative of a vector, I have to take the derivative of the magnitude as well as the derivative of the direction. And this is what we see today. This is the derivative of the magnitude. This is the derivative of the direction. And similarly, when we take the derivatives of the dot and the cross products, it also follows the product rule. For example, if I take a derivative of A dot B, this is, according to the product rule, A dot dB ds plus dA ds dot B. Same thing for cross products. So important thing to keep in mind that because unlike scalars that have only magnitude, vectors have both magnitude and direction. So when we take derivatives of vectors, we need to take derivatives of the magnitude as well as the derivative of the directions. Next, I'm going to introduce a very interesting term called gradient. Gradient, this is applied to a scalar, not to a vector. Now, what the gradient does is, let's say if you have a scalar field like temperature, and temperature is changing. If you are standing at a point, perhaps it is getting colder towards the top. If that happens, then we use the gradient to measure the magnitude and direction of the maximum rate of change of the scalar. And this gradient is calculated using the del operator. This is the del operator. Okay. So we apply this del operator on the scalar. Let us say the scalar is A. So if I want to calculate the gradient of a scalar, that will be del A, and that is given by the partial differential of A with respect to x multiplied by I hat, that is the unit vector in the x direction, plus the rate of change of A in the y direction multiplied by the unit vector in the y direction, that is j, and the rate of change of A in the z direction multiplied by the unit vector in the k direction. So the sum of the rate of change in the three directions, the vector sum, gives me the gradient. So the gradient of a scalar has both magnitude and direction. That is why the gradient is a vector, as you can see, I, j, and k. Okay, here. Now, you will see in textbooks that there cannot be a gradient of a vector. It's partially true, but and its outcome is a second order tensor, and like this term, but this is not very well defined in physical sense. So that's why I'm not going to discuss. The message is that a gradient is used to calculate the magnitude and direction of maximum rate of change of a scalar. Now, the next important term is divergence. So the divergence is calculated for a vector. There is no physically meaningful divergence of a scalar. That is why this is applied only on a vector. What it does is the divergence gives the magnitude of outflow of the vector from a point. So let us say if you have a 3-dimensional field and you have a vector like velocity, you go to one point, you see how much of velocity is outflowing from that point. And again, this is calculated by using the del operator. But here, because A is a vector, so we take the dot product of the del operator with the vector. And this gives us the divergence of a vector. So the divergence of a vector is the partial differential of the x component of the vector in the x direction, y component of the vector in the y direction, and z component of the vector in the z direction. Now remember that divergence of a vector is a scalar. So that is why on the right-hand side, there is no I, j, k. It is a scalar quantity. It does not have any. It only has magnitude, does not have any direction. If the divergence of the vector is positive, then we call divergence. That means it's outflow. If the divergence is negative, the opposite of that is called convergence, which is inflow. So positive divergence is outflow and negative divergence is inflow. I'll give you some examples. Like, if you look at the most left-hand side, all the arrows are pointing outwards. So that means there is divergence happening at this point. In contrast, if you look at the next figure, all the arrows are pointing inward. So that means there is convergence, which is negative of divergence. Sometimes it's like here it's very clear because all the directions are very clear. Either they are pointing inward or pointing outward. Now, what if that is not the case? Let us look at these two. So here, both the arrows are pointing to from the west to the east. But if I look at this particular point in the middle of the arrow, I will see that the vector coming from the west is smaller than the vector going towards the east. So that means less coming in and more going out. That means that is divergence. On the other hand, if I look at this particular example, here we see the vector coming from the west that is longer, and the vector going to the east is smaller. That means there is more coming in and less going out, which means this is a convergence. Sometimes it is, usually in nature, you will see it is much more complicated. There is motion in all possible directions. So visually looking at it, it's very difficult to tell. So in those cases, we are going to calculate, we are going to calculate the divergence using this particular formula, and we will see if it is positive, it is divergence. If it is negative, it is convergence. Okay. Now, the two more things. Next comes curl. The curl of a vector, that is a vector which gives the how much rotation is happening at that point. Okay. And it is measured by taking the del operator cross product with the vector. So let us say if I want to measure how much rotation is happening in this vector. We are looking at a vector field. We want to see if it is all straight or it is curved. There is rotation. So to measure that, we will take the del operator and take a cross product. And here we all know how to take cross products. So by using the determinant method, this is going to give me the curl of the vector. Okay. This is a measure of rotation, and curl, because it's a cross product, the outcome is a vector. That is why on the right-hand side, we have I, J, and K and the unit vectors. And the final term that I want to introduce is the Laplacian. The Laplacian operator is basically the second order differential. This is given by the dot product of the del operator, and this is the second order differential. So we can take a Laplacian of a scalar, and this is what it's going to look like. The second order differential of A along X plus second order differential along Y and second order differential along Z. And if I do the same thing for a vector, again, the second order differential along X, Y, and Z. The Laplacian can be both a scalar or a vector that is on the right-hand side. I can have both scalars and vectors. So what we have learned today is basically how to derive vectors, take derivatives of vectors, and then some special functions that allow us to measure special properties of vectors. Gradient, divergence. Gradient is looking at the rate of change of a scalar. Divergence is measuring whether there is incoming or outgoing. And curl, that is measuring the rotation, and Laplacian is the second order. So we are going to now use these concepts of the vector algebra and vector calculus to understand the forces in the atmosphere. Okay. Okay, I see there are few hands up, but because of the sake of time, I will not be able to take these questions. I hope you understand. You can post your questions on the chat, and the moderators will help you with, let me answer these questions at the end of the talk, okay? Okay, so now, if I want to describe atmospheric dynamics, I have to start with atmospheric energy. You know, we all know that the atmosphere gets all its energy from the sun. So incoming solar energy, but the atmosphere is mostly transparent to the incoming short waves. So the short waves get absorbed by the surface, and then some of it is reflected back as albedo. Some of it is radiated as long wave radiation that are absorbed by clouds and perhaps re-radiated either outward or downward to the surface. And heat lost by conduction and convection, that is what we call sensible heat, and heat lost by evapotranspiration, which is what we call latent heat. So that means, fundamentally speaking, that the atmosphere is heated from below. Even though sun is the major source of energy, the atmosphere is actually getting its energy, the direct source is from the surface. Now, when the energy is heating up the surface, the heating is not uniform. high latitudes get less heat, equator gets more heat. So the temperature at the equator is higher, surface temperature, land surface temperature in the poles is lower. Oceans have high specific heat, land has low specific heat. So that is why land surface temperature is higher, sea surface temperature is lower, even if they are at same latitude. So because of this differential heating, that it causes horizontal temperature gradient in the atmosphere, because different parts of the land surface are heated differently. And as a result of the horizontal temperature gradient, it creates horizontal pressure gradients. We know the process, very simple. Horizontal pressure gradients create horizontal and vertical atmospheric motion. So, and obviously vertical winds help precipitation, so that's why they are important. So everything is in this diagram, the basics of atmospheric dynamics. Everybody knows this. We also study this in physical geography when we are in school. So high pressure to low pressure, this is a very simplified diagram. There's a pressure gradient, so wind flows from high to low. There is convergence here. That is why there are updrafts, and this is where there are downdrafts. This is how typically an atmospheric circulation looks like. Now, when there are updrafts and downdrafts, the updrafts are pulled down by gravity, downdrafts are helped by gravity. And at every point, friction opposes this motion. So these are the three real forces that are playing on atmospheric motion. Again, this is a very simplified diagram. It's much more complicated than that in real life. And this is something you are going to learn as you go through the remaining 25 lectures. But now that we know the three fundamental forces, we can basically put them in Newton's law, the second law, which tells that rate of change of motion is equal to the sum of forces. In other words, if I want to calculate the acceleration of an air parcel at that point, I can do that by calculating the three different forces or the three different components of this acceleration. They are due to pressure gradient, friction, and gravity. So just three forces that gives me the total force that drives the atmospheric circulation. So we will start with them. Okay. So now, first, let me talk about pressure gradient force. Just give me 1 minute. I need to get some water. Okay. So first, we will discuss the pressure gradient force. Pressure gradient force is basically the surface force that acts on an air parcel. And let us try to understand using this example. I will again, as I've said, that will not be able to do all the derivations because of lack of time, but the derivations are in Holton or any other book. So take a look at this literature, understand the concepts, and then do the mathematics at your own time, okay? So now, let us consider this air parcel. And let us say its dimensions are delta x in the x direction, delta y in the y direction, and delta z in the z direction. And first, I'm going to look at just the 2x direction. And the area is del y, del z. Okay. So there is pressure in the x direction from west to east. Let us call this Px. And because pressure is force per unit area, so the total force here on the left face is Px times A. A is the area of that surface. If I look at the eastern side of the box, this parcel, then the pressure there is Px plus delta x, and the force on the right face is Px plus delta x. Remember, this is the Px is going from Px plus dx is going from east to west. That is why it's in the negative direction. So when I look at in the x direction and try to calculate the second law, then second law is mass times acceleration is sum of forces. And just looking at pressure gradient. Mass, if we assume rho is the density, so then the mass of this parcel is the rho times the volume, and the volume is given by A times delta X. A is basically delta Z, delta Y times delta Z. So this is the mass of the parcel. And let us say the acceleration due to the pressure gradient force in the X direction is APGFX. So mass times acceleration equals Px plus dx, delta x is negative, and Px is positive because Px is from west to east and x plus dx is from east to west. So this is giving me the Newton's second law in the x direction. Now, if I take limits, divide the right-hand side by rho a dx, the a cancels out. And what I am left with is acceleration due to pressure gradient force in the x direction is just 1 over rho del p over del x. So partial differential of p with respect to x multiplied by 1 over rho. Very simple, just take rho a del x, transpose it to the right-hand side. The two a's will cancel out and I am going to get this term. Fine. So this is only in the x direction. Now, if I sum up the x, y, and z directions, all of them, then the full three-dimensional pressure gradient force. Now, on the left-hand side, I only have the acceleration because I'm taking pressure gradient force per unit mass. That is going to be A is the sum of the force component in the x direction times the I hat, which is the unit vector in the x direction. Then the force component in the y direction times the unit vector in the y direction, which is j, and force component in the z direction times the unit vector in the z direction, which is k. And so when I look at this term and I try to recollect that what we learned just a few minutes back, this is nothing but minus 1 over rho times gradient of p. The outcome gradient of p, that is why that gives me the acceleration vector. So this is the acceleration due to pressure gradient force, or sometimes we loosely call that pressure gradient force because in the atmosphere, we always take things per unit mass. That's why this is acceleration and force we use interchangeably. So this is my pressure gradient force, minus 1 over rho gradient of P. Next, I am going to come to the gravitational force, okay? The gravitational force, as we know from definition that we have read in school, it's a constant due to gravitation times the mass of the two objects. In my case, because I'm looking at a atmospheric dynamics and we are looking at an air parcel, and r is the radius vector. That is the distance between the center of the Earth, which is our center of gravity, and the location of the parcel at any point. So r is the distance. Now, let us just consider the surface, okay? And if I say the radius of Earth is a, then the acceleration due to gravity at the Earth's surface, which is we call g0 star, that is nothing but acceleration is, remember, force divided by mass. So this is nothing but this term gmr by a square, where a is the radius of the Earth. Now, radius of the Earth, I'm sure you will recall it's like 3,800, some very large number. And if I think of the atmosphere, typically the atmosphere could be, say, 10 kilometers, little bit higher, maybe something like that, because in the stratosphere, the density is very low. You can go up to 20 kilometers. But again, whatever you take, 10, 20 kilometers, whatever you take, even 30 kilometers, it's less than 1% of the radius of the Earth. So I think we can neglect the height of the atmosphere and ignore the height of the atmosphere with respect to the radius of the Earth, then the acceleration due to gravity for any air parcel anywhere in the atmosphere, G star, can be considered, it is approximately equal to the acceleration at the surface. Now, we know the value of G. We know the value of m, which is the mass of the Earth. We know the value of A, which is nothing but the radius of the Earth. We can calculate this, and this becomes 9.805 meters per second square. That is why we in the atmospheric dynamics or meteorology, weather and climate field, we consider gravity to be constant. Obviously, we know gravity varies between the surface equator and the pole. It varies whether you go deep into the Earth or you go up into the... For all practical purposes, we can take it to be constant as 9.805. Okay. Then I come to my third force, which is viscous force. This is basically friction. So what happens is that whenever there is a flow in a fluid, some of them are flowing faster, the others that are attached to the ground or to a static surface, they are flowing slower. So they are internal molecular interactions that tend to resist the flow. This is called the viscous force that causes what we popularly call as friction. Now, again, I will not go into the derivations, but just explain to you how it works. So let us say that this is, again, I take an air parcel and there is stress across this parcel. Where is the stress coming from? Let us say that if the parcel is near the ground, at the ground, the velocity is 0. As you go up, the velocity is higher, so there will be a stress. And the stress is typically, we use the Greek letter tau to measure the stress or to express the stress. So first, I'm going to just look at acceleration in the x direction. And let us just consider the bottom and the top faces. Let's say the bottom face is slow, the top face is fast. And so because of this stress, we have a stress which is tau zx, okay? And this acceleration is given by 1 over rho, the partial differential of the derivation. Again, I'm not going to be able to do it here, but as you can see, it is just the slope of the stress that is giving me the acceleration. Rho is coming because I am dividing everything by rho, so that instead of force, we can look at acceleration. So this is my acceleration in the x direction due to stress in the z direction. Now, the acceleration in the x direction can be caused by stress in x, y, and z in 3 directions. So, but very importantly, we have done experiments and we have seen that this term stress, tau, that is a function of the flow. That is, tau is given by mu, which is a constant and is called the dynamic viscosity coefficient times the gradient of the velocity. In other words, the acceleration, which is a differential of the stress is again a differential of u. Okay, so we take velocity, take its differential, that gives me stress. We take the differential of the stress, that gives me acceleration. Therefore, the acceleration can be represented as a second order differential of velocity. And this is how this is done. That acceleration in the x direction due to stress in all 3 directions is given by mu. Mu is mu over rho, which is the kinematic viscosity coefficient. That is equivalent to nu times the Laplacian of u, only in the x direction. And when we add them up, the del square of u plus del square of v plus del square of w in the 3 different directions, that tells me that the acceleration due to viscous force or friction is given by nu times Laplacian square or Laplacian of v. So pressure is a function of gradient, first order differential, but viscous force is a function of the second order differential of velocity. So now interesting thing is that we have already used both the gradient and the Laplacian concepts that we have learned earlier. So now time has come to put together the Newton's law for the atmosphere. This is the acceleration is given by, okay. So the acceleration is given by the sum of the pressure gradient force, the gravity, and the friction. Okay. So this is the Newton's law. However, it's not going to be that simple for us. Okay. And let me explain to you why. There are something in the atmosphere called apparent forces. Okay. The Navier-Stokes equation, that is basically the Newton's second law of motion for the atmosphere. This equation is valid for inertial reference frames. That is, we all know what is an inertial reference frame. It is a static reference frame. However, when we are measuring velocity, we are measuring it with respect to the Earth. When we are looking at the position of a cloud, for example, we are saying that, okay, the cloud is over this particular latitude and longitude. So all our observations are relative to a rotating reference frame. How can we apply a fundamental equation like Newton's law if all our measurements are on a rotating reference frame? That is why in Navier-Stokes equation, we require some correction terms, because Navier-Stokes equations are applicable only for inertial reference frames. Okay. I'll give you one example here. Okay. Let us consider, this is an example that this is a diagram that I made when I was teaching at Illinois. So I was using examples from the United States, and that is why just bear with me. Let us say this is the Earth looking up from the top. This is America, North America. This is Greenland. This is Europe, and India is right here on the other side. So there is a cloud which is sitting over Chicago, this gray patch. Okay. It's stationary, but the Earth is rotating. So now after some time, if I look at this, the Earth continues to rotate. So North America, from here, it is continuing to rotate, but the cloud is still sitting at the same location. So an observer in Chicago is looking at the sky and saying it's cloudy. The cloud is not moving. Only the Earth is moving. And similarly, like, we started here at the beginning of the thing, and then we started continuing to rotate. Let us say we've come here. The cloud is still over Chicago. So to an observer on the Earth, the cloud is stationary. However, if I am observing this from the sun or from a near inertial reference frame sitting outside, it will appear to me that the cloud is moving in an arc. Okay, so and it ended up here. So that means a cloud that appears stationary to an observer on the Earth will appear to be moving in a curved line to an observer from an inertial reference frame. I'm going to give you another example. So are you able to see my screen? Is there any issue?
No, we can see, sir, everything.
Okay, thank you. Thank you. Okay, now we are going to look at a moving cloud. Okay, so let us consider this again, same situation. And there is a cloud which is situated here over Italy. And let us say the cloud is moving in a straight line from east to west. Okay. And again, as the Earth is also rotating, so the cloud has left Italy, it is moving over the Atlantic Ocean. Now it has moved to near Greenland, and the Earth is rotating again. So the cloud has moved to over North America. Now the cloud is over Alaska. Now the cloud is over Pacific, and the cloud is deep into the Pacific. So it started over Europe, went to the Pacific. The cloud is moving. So now, if I'm observing this cloud from the space, from an inertial reference frame, then the cloud is moving in a straight line. However, if I look at the location of the cloud and map its latitude, then the cloud is moving in a curve. So very important, right? That when I look at a cloud that appears to be stationary from an observer sitting on Earth, the same cloud to an observer sitting in a inertial reference frame outside, the cloud appears to move in a curved line. But an observer who is sitting outside on an inertial reference frame and sees a cloud that is moving straight, that cloud to an observer on the Earth is moving in a curve. So this is why when we look at satellite images, we need to reinterpret them so that we are able to reconcile them with our observations taken on this Earth. I will show you one quick animation to tell you how, like, this is an interesting animation that shows how things change as we go up on a rotating platform. So here you will see that there is a rotating platform, and there are two scientists who are sitting on two ends of this platform, and they are trying to throw balls, okay, and trying to catch. And the platform is rotating. So initially they were able to catch the balls, but now they are not able to catch the ball. So let us look at it from the top, okay? The camera is mounted to the ground. That means the camera is inertial, okay? So they are throwing the ball straight, yet to the right. So when you look at this, the ball is going straight from the left hand of your screen to the right hand. So the ball is traveling. It is like the cloud that is traveling in a straight line. Okay. And now the camera is mounted on the rotating platform. So now you see that to the camera, the ball seems to be curved. So this is the difference. When the ball is seen from an inertial reference frame, it is straight. When the ball is seen from a rotating reference frame, it is curved, just like the cloud example that I gave you earlier. So this is what is happening, is that in the rotating reference frame, the ball is thrown straight, but to you, it seems like it is getting curved. So that's nothing, like there is no force, nothing. The ball is actually in an inertial reference frame going straight. However, to a rotating reference frame, it is curved. So now, in order to account for the rotation, we need to have some correction term. So a derivative in an inertial frame is the derivative in a rotating frame plus correction due to rotation. Okay. And what I mean by that, like let us say we look at this particular vector. The vector is in red, where we have X, Y, and Z, 3 coordinate indices. Now let us say I slightly rotate this, the reference frame. I'm not changing the vector in any way. Its magnitude is the same. But the reference frame is rotated. So obviously the vector goes from here to here. And because the vector is basically has both magnitude and direction, because of this rotation, there is some acceleration in the vector, only in the directional sense, not in the magnitude sense. So that acceleration is the correction due to the rotation, right? So this is the original vector. The magnitude is the same. I have rotated the axis. Now the vector is pointing to a different direction. So now, again, I'm not going to do the derivation, unfortunately, because of lack of time, but it has been seen that the derivative in the inertial frame is equal to the derivative in the rotating frame plus a correction term, and the correction term is given by omega cross A, where omega is the angular velocity. Okay, so that is the correction term due to account for the change in direction. And that's where omega comes in, where omega is the angular velocity. Now, instead of A, let us take the position vector, okay, R. So the absolute derivative of the position vector is the relative derivative of the position vector times plus omega cross R. Now, the derivative of the position vector is nothing but velocity. Therefore, absolute velocity is relative velocity plus omega cross R. Now, let us take the derivative of absolute velocity, okay? So, if right here, instead of A, I am going to use velocity. So, again, the derivative of absolute derivative of velocity is the relative derivative of velocity plus omega cross V. Now, V here is VR plus omega cross R. So I substitute this in my equation, and what I end up with after simplifying is that the absolute derivative of velocity is the relative derivative of velocity plus 2 omega cross V minus omega cross omega square R. That means velocity in an inertial acceleration in an inertial frame equals acceleration in a rotational frame plus 2 omega cross V minus omega square R. This omega cross V is to us known as the Coriolis force, and omega cross R is known as the centrifugal force. This is where they come from. These are nothing but correction terms which account for the fact that my coordinate system is rotating. That is why when I use Newton's laws of using measurements from the Earth, it does not work because our coordinate system is rotating. That is why we have to add a correction term. So the Newton's laws of motion in a rotating frame now becomes the relative velocity. That's all that we are interested in because all our measurements are in relative to the Earth equals pressure gradient force plus gravitational force plus friction plus the Coriolis force and the centrifugal force. Now, if I write the Navier-Stokes equation, which is a customized form of this Newton's second law just for atmospheric sciences application, weather and climate application, we note that all observations are relative to the Earth, and that is why we are not going to use the subscript R. And also, often what we do is because centrifugal force works nearly in the vertical direction, we club it with gravity and we have something called effective gravity. So this is now my Navier-Stokes equation. That is the acceleration of any air parcel is a sum of the pressure gradient force plus effective gravity, which is the sum of gravitational acceleration and centrifugal acceleration, and friction and omega 2 twice omega cross V, which is the Coriolis force. So with that, I took 47 minutes. I'm going to stop here and I'm going to take questions. Thank you.
Thanks. Yes, thank you, sir. Before we take the questions from the Q&A session, we would request all the panelists to switch on their cameras. We'll quickly take a photo. Also, I would request sir to unshare the screen so that we can, yeah.
Yes.
Bhaskar Rao sir is, yeah. Mrunal is here. Mrunal, can you take? Yeah.
Baidya sir, namaskar. Mr. Bhaskar Rao, sir, he is not visible.
We took, sir.
Okay. Like,
So, Mrunal, please take. I request Mrunal to take over the question answers.
Okay.
Good afternoon, sir. Thank you for the nice lecture. It was a nice lecture covering our basics again. So there are some questions. The first question is for Anush Raghanuram. He's like, is there a clear relationship between incoming solar radiation and tropical waves?
Sorry?
Sir, is there any clear relationship between incoming solar radiation and tropical waves?
Yes, obviously, but can we restrict the questions? These are things that are much advanced topics. So I think that many of I mean, I understand many of you are at different stages in your career. So perhaps if we can keep the questions, if that's okay, questions kind of focused on the topic that we have done today. So
Yeah,
Yes, sir.
clearly,
I've given the message. I've given the message
Yeah.
already that please ask questions related to today's lecture, not irrelevant questions, whatever comes to your
because
mind.
yes, some people are perhaps beginning at the beginning stage of their career, some are at later stage. So
Yeah.
if we can focus on the topic at hand, that will be the most useful to everybody.
Yes, sir. There is another question. Like while calculating forces on an air parcel, why it is always calculated assuming the air parcel to be a cube and not a sphere, whereas in case of cloud physics and aerosol physics, it is a sphere in almost every cases.
That is a very, very interesting question, actually. Well, I mean, actually, the thing is that, so because we follow the Cartesian coordinate system, so that is the oldest, one of the oldest coordinate systems. There were rotational spherical coordinate systems also for a long time, but most of the equations in fluid dynamics and geometry were developed using the Cartesian coordinate system. And in the Cartesian coordinate system, as you know, that there are x, y, and z direction. So that kind of a cube kind of fits right in. These kinds of equations can also be derived in spherical coordinate systems. And many advanced mathematics books, especially in dynamic meteorology, have derived these equations taking the spherical coordinate system. So, but they are equivalent. Even though we start from a Cartesian coordinate system and we derive equations for a kind of cube-like air parcel, and from that, now today I showed you that how you go from an inertial reference frame and then you have to add correction terms to go into a rotational to account for a rotation of the Earth. Similarly, the next step, which I think perhaps will be covered in a later lecture, if not definitely in the modeling courses, it will be covered, that how to account for the sphericity of the Earth. So we will take the same Navier-Stokes equation and we will add correction terms to account for curvature. So no, you are absolutely right that we do not start with curved or cylindrical, or actually, why not cylindrical? Because the equidistant projections map that we always use, it's based on a cylindrical projection. So many different shapes could be done. But eventually, I think that all the equations will, people have done it, I have not, but many people have worked on this. And so the equations eventually become the same. So I think that it is just historically, we started deriving everything in the Cartesian system. That's why.
Yes, sir. There is another question that how that forces affects climatical condition on a particular places.
Oh, okay. So, I mean, if you look, so climate is basically a long-term average. Let us start with that. I will try to give a very basic answer. Okay. For almost a beginning student, that so if you look at the location that where you are in, so climate is a function of both all dynamics, also thermodynamics, and also microphysics. We are talking about motion. Thermodynamics is about temperature, how as a parcel is moving, it's expanding, cooling. And then microphysics, where as it cools, phase change or warms, phase change happens. So so it's much more complex than dynamics. But if we look at the fundamental, the atmospheric dynamics which drives the fundamental flow of the atmosphere. Okay. Not only in all locations, that is one of the major drivers of climate. So let us say, for example, like, if you think of this, the equator is always warm and the poles are always cold, right? Because of the shape of the earth and the tilt of the earth. So that is why there will always be a pressure gradient. From the equator will have a low pressure, poles will have high pressure. So there will always be some sort of a flow from the poles to the equator. Now, if you look at the single cell model, the very primitive model of the earth, the circulations are driven by nothing but pressure gradient force. If you look at the more complicated modern models, the three cell model of the earth, pressure gradient force is a driver. So I can clearly say that if you are at a particular location, the large scale pressure gradient in your location, the pressure gradient force in your location is the primary driver of motion in your location. So that way, your climate will be governed by the large scale flow. Now, I'll give you one example. Say, for example, if you look at now perhaps I will not answer this and give it to you as a question, that if you look at most of the deserts, Sahara, Thar Desert, this and that, across the globe, they are more or less at the same latitude. Perhaps, after a few lectures, when you learn about general circulation, you will see how something as simple as the pressure gradient force has caused that phenomenon. Okay. So you will find that out. I'm not going to talk about it, but definitely, as you can see, that pressure gradient force and Coriolis, the two major forces, you will see responsible for this spectacular pattern that all the major deserts are in similar latitudes. So in other words, that forces are one of the primary drivers of climate in your region.
So there is another question. Is there any physical or gradient, or it just to get the change in quantity?
Well, change in quantity, yes, or I would not say just the change, but it is the rate of change. Okay, so I think that is the physics. Okay, so for example, why is rate of change important? Not just the change. Okay, which means that if you look at it is gradient delta P over delta X, right? Or delta P over delta Y, not just delta P. So very important. Let us think of let us say if you are in a coastal region, you are over land, the temperature is high. Over the ocean, close by, the temperature is low. So over land, the pressure is low, temperature, and over ocean, the pressure is high. So this is delta P. And delta P divided by delta X, that causes a pressure gradient, that causes a sea breeze. Similarly, if you look at the world, temperature of the equator is high, temperature at the pole is low. So there is delta P, right? There is high pressure over the pole, low pressure over the equator, there is delta P. But the delta X there is very long, it's thousands of kilometers. So that is why the delta P over delta X is smaller. So when you look at the gradient, you should not just look at the difference in pressure, but look at the difference in gradient. And that is the physical meaning. The gradient drives the motion, not just the difference.
Okay, so there is another question. Is there any connection between atmosphere dynamics and real observation, and how it will be impacting it?
So I'm not clear about this question. So dynamics is a way to explain the real observation. Any science that we do, especially in atmospheric and oceanic sciences, which are very applied sciences, you can think of geology or any kind of physics. So physics is just, this is kind of like connected with physics and mathematics. This is just to explain why things are the way they are. Now, I showed you one animation at the beginning of my talk. There I showed that near the surface, if you look at the flow, you will see lots of cyclones and anticyclone. As you go high up, like at the top of the atmosphere, the flow is not circular anymore. It's just straight. It is parallel to the latitude and longitude. It's either going from west to east or going from east to west. Why? This is an observation, right? Now, dynamics through mathematical treatment using forces like, different concepts like what we did today will be able to explain why things are the way they are. So that in my mind is the connection, that whatever you observe, so the basic thing for the basic driver actually for all science, in our field, like, physical sciences I'm talking about. Mathematics can be very abstract. Philosophy is very abstract. But in physical sciences, how they came about is that people observed certain things. And then they tried to think, why is this happening? So asking the question, why? That is more important. So I will tell you that, it may seem that, okay, today we derive some equations. What is the connection with real life? The connection is that once you are able to observe something, you appreciate the beauty of it. There is, I'll just give you one example, right? Think of 100,000 years back, primitive human being. They are looking at the moon, and on a full moon day, it's very beautiful. On a dark moon, on a new moon day, it's dark. So that is an observation. So human beings started thinking that why is it bright, or why is I can see the moon on one day, then after 28 days, the moon is dark. So that thought then led to the birth of the science of astronomy, right? So most of the sciences, definitely true for our field, it all started with human beings who observed things but did not stop with observations. See, an artist looks at a moon and paints a picture. A poet looks at a moon and composes a poetry. A singer looks at the moon and sings a song. Scientists, we look at the moon and ask, why is it the way they are? And so,
Yes.
to all of you who are kind of trying to make sense of atmospheric dynamics, I see that I will tell you, look at the observations and ask yourself, this looks strange or this looks unusual. I want to find out why this is happening. Then I think what you have learned today, or you will learn in your classes of dynamics and thermodynamics and microphysics, you put them together, that knowledge, and you will explain it. There are many, many unexplained phenomena in the world today. Many things we don't know. We observe them, but we don't know. So use the observations as a starting point and use the mathematics and the physics that you learn in the class to explain those observations. That is the connection.
So there is another question by Dr. M.G. Manoj. It is known that Coriolis force is apparent force, which does not change the magnitude and speed of flow, but only changing direction. However, there is Coriolis force appearing in Navier-Stokes equation, which of course has numerical value corresponding to omega and v. Doesn't it mean that this term changed the magnitude of the acceleration?
Yes, a very important point. Yes, obviously, the Coriolis force changes the acceleration, right? If you look at the equation, there is Coriolis in the Navier-Stokes equation. But because that is perpendicular to the direction of the flow, it changes only the direction. It does not change the magnitude because it is only in the direction. The Coriolis force is an apparent force, as we see that it is a correction term that comes into the picture because we are trying to apply certain laws that are valid for inertial reference frames to observations that are valid only for relative reference frames. And our relative reference frame is a rotational frame. So that is why it comes as a correction term. So it changes the direction of the flow, but it cannot change the magnitude.
Yes, so there is another question by Krishna Priya. She is saying, thank you for the wonderful lecture. The question is, the Navier-Stokes equation and equation of motion are being discussed separately. If someone were asked to write equation of motion and Navier-Stokes equation, how would we represent it? What is the major difference between them?
Okay, thank you, Krishna Priya. So, no, they are basically the same because the equation of motion comes from, is basically Newton's second law, which tells us that acceleration is which is the rate of change of momentum. So equals the sum of forces. In other words, if I divide both sides by m, then I get acceleration is the sum of three different accelerations. And real accelerations and two apparent accelerations, Coriolis and centrifugal. So these terms come. So if you in any Cartesian, any coordinate system, for a general application, then you can use the inertial reference frame, that three forces. But the moment we are talking about the Earth, so then I think it is better to use the Navier-Stokes equation. Navier-Stokes equation is widely used in fluid dynamics, because it is able to explain bring in the correction terms. That is why it is much more directly applicable to us. So I think that if someone asks you to write, and I think from an exam point of view, if you just write the fundamental Newton's law version with the three real forces, then they will think, oh, Krishna Priya doesn't know. But that is why I think, to be on the safe side, you will say that, no, I know the science, so I'm going to tell you the Navier-Stokes equation, which is the fundamental equation, but corrected for rotational reference frame and more applicable to the atmosphere and the ocean. So that would be my suggestion. But I think someone who is setting question papers should, like, UGC, CSIR or something, should be mindful of that.
So there is another question by HGPA Ratnavera. The formulation identify the changes of moving parcel.
Sorry. I think I see what you are saying. Yes, the properties of a parcel changes. The properties of a parcel changes in the sense, let us say when we have a parcel near the surface and it is rising up and down. But, so the mass remains constant. So what changes is basically the temperature due to expansion, the volume. Then these are not affected, then the equations are fully applicable. If it is just expanding and contracting, as a parcel is moving up, no, this pressure change aloft or moving up and down, because in response to the pressure change, the parcel will become bigger or smaller. And then by gas law, PV equals is a function nRT, or P equals rho RdTV, whatever. So the temperature will change. Fine. That is not going to affect any of these equations. However, you need to be very careful that, let us say, if the temperature changes and there is water vapor in the parcel, and let's say the water vapor condenses and becomes rain, and the rain falls out, then the mass of the parcel will change. In that case, your equation, you have to account for the change in mass. So that's the only thing. However, typically in the atmosphere, the mass of water vapor is small. And most of the time, like, the models that are able to, they have sophisticated microphysics schemes that are able to take care of the change in mass at different levels. Most of the models are actually not Lagrangian, they are Eulerian. So they treat this change differently. So I will not go into those kinds of details. I think that you will learn later in the numerical modeling lecture series. But all that you need to know, that because in a parcel, the mass of the parcel is assumed to be the same. So that is why the equations of dynamics can be applied to them even while they are moving. Only thing that changes is the volume. And if you look at the equation, then you will see that, like, we are not accounting for any kind of condensation and dropping rainfall or scavenging, precipitation, other things.
Thank you, sir. There is another question by Dr. Era Upadhyay. Thank you, sir, for the insightful lecture. He want to know how centrifugal force helps to simulate gravity in rotating space stations.
Sorry? Oh, how? Centrifugal force? Well,
helps
I mean,
to?
in space, okay, I get it. So space stations, I mean, centrifugal force is pointing outward. It's a very small force, actually, compared to gravity. So on the surface, it's really, really small. It's in the direction of gravity. When you are away from the surface very high, then it is a very important factor. That is why, if you do not add additional forcing by, thrusters or the fuel or something like that, then you are in a danger of kind of getting lost to space. So all of these things are taken into account when people calculate and put one satellite in a particular orbit. So definitely it's a factor which we use when we calculate the exact where to put our satellites. If you look at low orbital satellites for use for cellular cell phones and other things versus geostationary very high, so they all have taken centrifugal force into account.
Yes, thank you, sir, for the answer. There's another question by Farno Shadar. He want to know the difference between viscous force in atmospheres and viscous force in ocean.
Oh, yeah. I mean, it's basically the same. Just if you look at the coefficients, so viscous force as such, it's basically just the second order differential of the velocity but it has something called the coefficients, the viscosity coefficients. So mu and rho, both of these are different in oceans. So that is why the viscous force in the oceans, in water, is much larger than the viscosity in the atmosphere. Also in the ocean, density is affected by salinity. So you have to account for not just density of the air, but also salinity that affects density to calculate the forces. So
Yes.
just two terms, the kinematic coefficient and the mu, the viscosity coefficient, and rho, the density. These are the two factors. Once you put them in the equation, this equation is applicable for oceanic motion as well.
So moving towards the next question, are Coriolis force and centrifugal force equal?
No, Coriolis and centrifugal are different forces. They work in different directions. Coriolis, if you look at this, it's omega cross V. So that is why, remember cross products, right? So that is why its direction is in the horizontal direction mainly, and in the vertical, it's almost non-existent, very small, the coefficient. However, centrifugal is mostly application-wise. So, I mean, there are, for all practical purposes, Coriolis can be considered a horizontal and centrifugal is a vertical, because the horizontal component of centrifugal is very small. The vertical component of Coriolis is very small. So they act in different directions.
So the next question is by Raja. Based on curl of a vector, can we classify the rotation as micro or a meso major of rotation?
No, I will not say that. The micro and meso, the classical definition is a matter of scale. So micro is small scale, mesoscale is larger scale. So if you look at mesoscale eddies, that there are lots of microscale eddies also in them. Okay, so I would not look at the magnitude of the curl and try to define whether it's meso or microscale. I think you should look at the spatial pattern and from that try to ascertain whether this is meso and microscale. Or take perhaps average over a large area or something like that to calculate what is the spatial scale. Curl just gives you the strength of the rotation. The magnitude of it, a large microscale eddy and a large macroscale eddy and a tiny microscale eddy may produce similar magnitude of rotation. So magnitude of curl is not, it's just a measure of rotation, but not a measure of the spatial scale.
So moving to the next question. How does the Coriolis force affects aviation considering the variation of Coriolis force with altitude?
So, as I said, that Coriolis force, I mean, does not have a vertical component, but because it's omega cross v, so as we go higher up, normally we know that velocity increases. Typically, I mean, there are obviously like many different complex patterns, but generally, so that is why the magnitude will increase. And no, everybody takes into account Coriolis force. Everybody, definitely in aviation, this is taken into account. I will give you another example. So when I was teaching at Illinois, even here at IIT, we have lots of students who are from the armed forces background. We have mostly Air Force and Navy who are here. When I was teaching in Illinois, because meteorology is a very popular field in the US, it is actually the second most, in terms of job point of view, career point of view, meaningful major after mechanical engineering in the US. So lots of people come to study meteorology, including from TV to people in disaster, weather forecasting, climate, and large contingent of armed forces personnel, okay, from both all Army, Navy, and Air Force. I've had, over the years, I have taught many students. Tyagiji himself is from the Air Force background. Now, so what I was told, and I did not know this, that some of my students were taking sniper training, where they shoot rifles in the army over long distance. So they are taught about Coriolis force and how much will be the deflection. So when you're shooting an enemy from a long distance, you have to take Coriolis force into account. So Coriolis force is very, very important. With everybody, like who is interested in any kind of fluid, anything in the atmosphere, or ocean, including aviation to defense, a missile, all of these things take into account Coriolis force. Now, how exactly, that is up to you. Like, you are at a location, how far your target is, or how much distance you are going to travel, how much fuel loading you have. So these complex calculations are made by a computer to tell you how much acceleration you have to put if you want to go in a straight direction, so that you don't veer with respect to the Earth from your trajectory.
Yes, thank you, sir. Just two more questions to go. The first one is, why is centripetal force not accounted for in the momentum equation?
Actually, I mean, I think I talked about it, but I did not go into the details. So when you look at a book like Holton or Martin or something like that, you will see the derivation. So what happens is centrifugal force works almost in the vertical direction. So that is why if I mean, you will get a copy of the lecture, you will see that in the momentum equation, we do not use gravity. We use something called effective gravity. Effective gravity is the sum of gravity and centrifugal. Gravity is pulling you down, centrifugal is pulling you up. So the value of 9.805 that we tend to use, it's actually should be a slightly smaller value to account for the centrifugal force. You don't see in that equation because it is clubbed with gravity to make something called effective gravity. So it is in the equations, but hidden in the gravity term.
Thank you, sir. The last one is from Dr. M.G. Manoj, sir. That you mentioned that the delta represents the maximum gradient. Why should it represent the maximum gradient? Shouldn't it be simply a gradient only?
Yeah, so, okay. So basically, remember, we are talking about, like, say, a three-dimensional field, right? So if it is one-dimensional, that let us say temperature is changing only in one direction, then gradient is just one direction. It is the rate of change in that direction. But now let us say there is variability in both X direction and Y direction and Z direction. Then how do you account for variability in all three directions? That is where gradient comes in. It tells you what is the maximum variability in which direction and what is its magnitude. So we use the word term maximum because it's the sum of gradients in three. So it's a resultant. So that is why, because we are talking about three-dimensional fields.
Yes. So the last one is from Krishna Priya. She is asking, we consider the Coriolis force as a pseudo force, even though it exists. Why is this so?
Yeah. So, again, that is the thing, that if you are in an inertial frame of reference, there is no Coriolis force. However, Coriolis force is basically just a correction term. Okay, we just name it as a force or an acceleration. It is a correction term that we add to the equation to account for the fact that my equation is applicable for inertial reference frame, but my observations are in relative reference frame. So when I am measuring velocity, let us say of an air parcel or a car, if someone saying is that Krishna Priya is traveling in a car at 60 kilometers per hour, you are not traveling at 60 kilometers per hour. You are traveling at 60 kilometers per hour relative to the Earth. So if I write an equation of motion for your car from an inertial reference frame, I have to account for both your motion, the velocity of the car, and the velocity of the Earth. So then that's why I need to add a correction term. And the Coriolis force is nothing but a correction term. So that is why we call it a pseudo force.
Thank you,
Okay.
sir, for answering all our questions. So here the session of question answer has been ended. Now I hand over to Rohini ma'am for further.
Thank you, sir. It was a wonderful session. So thank you, Mrunal. Before going to the vote of thanks, which is a formal vote of thanks, I would like to say, sir, you have really given a wonderful lecture. We have received almost 250 feedbacks from the participants, and everyone has rated it as very good and excellent. So I also felt that it was like revising whatever we had learned before. So very nice.
Yeah, I also wrote it even in the group. Means I'm usually missing your lecture in summer because I learned from the same institute, but maybe it would be better if I could join a little later. Then I could attend your dynamic methodology class.
Really nice, sir. Yeah. So thank you very much, sir. I would also request you one more thing. There are many questions regarding the references and books to refer. So if you can add one last slide in your PPT about the different books they can refer and then send us, it will be really great, sir. So I can make a PDF and then circulate it to the participants. So official vote of thanks. I would like to thank first the speaker, definitely,
Dr.
for
Rohini,
keeping. Yes, sir. Yeah.
In the brochure, all the people, all the participants have received the brochure. And in the brochure, we have given the list of the references, the books to be referred for this entire dynamic meteorology lecture series. So all the participants are requested to look at those references and please read those books, okay?
Yes,
Yeah,
I
please.
think yes, I agree with Dr. Dash because I have only used fundamental books and added that with kind of only just explained it differently. So there is no new science here because this is very fundamental. Perhaps if needed, a book on vector algebra can be added like Shom series or something like that, if at all. Yeah. So I think the list is very, very comprehensive.
Okay.
Anyway, I should say that all the participants are really, really very lucky to attend the lecture of Professor Baidya Rao. He has made a tough subject very simple, I should tell you. Very tough subject explained in a very simple way. So thank you.
Thank you, sir. So I would really thank the speaker first for keeping us glued actually to the screen. And every time I saw the participants didn't go anywhere, the number was only increasing but not decreasing. So definitely everyone was very happy to attend. Also, I would like to thank Someshwar Das sir, our secretary, for his welcome address, and Dr. Mili Ghosh to introduce our speaker. And definitely Mrunal, she's also a student with us here. So she did this question and answer session for the first time and very good. So thank you, Mrunal, for that. And all the other panelists, Dr. Swagata, Divya, Dr. Aditi, Dr. Bhatia sir, and Kai Ling Wu. So thank you, everyone. The next lecture will be on 1st of February, and it will be delivered by Dr. Akhilesh Mishra from NCMRWF. And the topic is vector equation of motion in an absolute and rotating frame of reference. So please join around 2:40 p.m. on next Saturday, that is 1st of February. Anything else, sir, we would like to mention?
Formal vote of thanks in today's program or no?
Oh, that was the vote of thanks formal.
Okay,
Just
fine.
doing my
Yeah,
job.
now
It's okay.
we made it short actually.
We made it short
Yeah.
because every time it
Yeah,
takes
like,
long
very-
time. So this time,
Based upon the feedback, many people have given feedback that please just be confined to the lecture rather than making it more formal.
yeah,
And vote of thanks. So otherwise, people start going away, leaving the lecture. So yeah, fine. Yeah, that's good enough. Yeah, thank you so much. In fact, for all these things. And by the way, most participants should know also that Professor Baidya Rao is also the member of our advisory panel of this entire lecture series, right? And he has given wonderful inputs for designing the syllabus for this lecture series. So we would all like to thank him once again for that. Thank you so much.
thank you, sir. So I will close the meeting and thank you again, sir, for such a nice lecture. So good evening, everyone.